Good morning, gentlemen. No ladies here. Oh, almost. Oh, Teresa, yes. Good morning, lady and gentlemen. As usual, mostly no ladies. And as usual, nobody here for the front of stage, mosh pit in the front. Everybody's shy, sitting back, yeah? Okay. Welcome to my presentation. I don't know actually how it is officially called on the website. I don't remember, to be honest. For me, this one is called, however it's called, I don't know. Now it doesn't work anymore. What happened? Okay. For me, it's to talk about stability of temporary structures. And stability is usually gained by ballast, cantledge, counterweight, however you call it. And in order to explain what we are talking about, I would like to start with 3 videos showing what happens when the ballast is not properly existing. So the first one looks kind of funny. It's quite old, the resolution is not very good. He's enjoying his steak. And this happens when something is missing. The next one, a huge scaffold wall with a relatively small LED screen on it. And the last one is a video from the Indiana State Fair in the United States. Probably I have to give a trigger warning. If you feel better to close your eyes, there will people die. So this is what nobody of us would like to experience, I guess. By the way, right now I just forgot to introduce myself, which I should have done in the beginning. My name is Norbert Tripp. I'm the technical director of Area ProLight and Lightech. And we have as well some additional brands for chain hoists, for stage stacks, for load cells, and that should be enough. No, I have to tell as well that I'm a structural engineer, and I'm working within the event industry as a structural engineer since almost 20 years already. Okay, but that's it. Now let's have a look on a quite small roof structure in the style of a saddle roof. It has 8 by 6 meters. And the question is, what happens with this structure when the wind is blowing into the open front? When it's blowing to the side or on the back side, it is comparable, but slightly different, just due to different aerodynamic effects. But the most simple way to start with is when it's going into the open front. So the wind is blowing in. Let's switch. Then the question is, what gives the stability, or what means stability of a structure? And the stability is not given anymore when one of 3 different failure mechanisms occur. And these 3 failure mechanisms can be uplifting, or overturning, or sliding. And let's have a look on the uplifting. The wind is, so this is the side view. The wind is blowing into the open front. The wind is captured by the closed rear wall and the closed rooftop, and it's pressing horizontally and it's lifting up. So the vertical parts, or those parts of the forces that occur on the structure, which are vertically upwards, want to lift everything up. Then overturning means that the wind is blowing in, and on the rear wall, all these forces are collected to a center, to one resulting load in half of the height, which has a horizontal direction acting this way, and it will overturn around this bottom rear base. All the parts in the vertical, under the horizontal rooftop, are acting vertically here, and they have a lever arm to the point of overturning. That means everything turns over. Finally, sliding. So the wind is blowing in, the force is generated, and the horizontal parts create a sliding effect of the whole stage. So the question is now how to prevent this. It must be prevented by some kind of counterweight, ballast. Then it's the question, how much ballast is this supposed to be? This is now a simplified calculational model. You don't see real truss, so all the diagonal members in the truss are missing, because basically the model or the trusses are reduced in the calculational model to one single line, and whatever force is applied to this single line, or whatever internal forces, that means shearing, bending, and axial force, are in that member, are then translated back to the capacities of the truss. So, when the wind is blowing, this is the reduced model, just by lines, and then the forces are applied by linear representations. And you have here on the side wall, for example, there is 1 kilonewton acting from inside the roof to outside. It is a linear load, and then it's decreasing in a triangular shape to 0. And it symbolizes the force that is applied from, let's say, this part of the side wall, which is connected to that tower. Additionally, the membrane, the canopy, the scrim, however you call it, is connected between the towers and the side truss, and it's blowing out, so it creates a bubble, and the curve causes a tension force in the membrane, which pulls the towers together. And this is why there's in support forces down at the bottom at the bases, because it is a static rule. As soon as you have an action imposed to a structure, it causes a reaction. And the support forces are nothing else than the reaction of the imposed loads. Now let's have a look on the front left base. There is a vertical uplifting force of 15.6 kilonewton, which equals 1.56 tons, roughly. And a horizontal 14 kilonewton acting. It is shown towards the front, but as it is the reaction, the action itself is that this base has the tendency to slide to the back. The arrow just shows the reaction, which means it is in the opposite direction of the acting load. And there's a small 400 kilogram pushing outwards. So when now you want to calculate how much ballast do you need in that front base, we have these three different forces. So there's 15.6 kilonewton lifting up, 13.9 pushing to the back, and 4.06 to the side. Let's have a look on the uplifting part. we have to put there some ballast to make it heavier, at least the same amount as the uplifting force. That means at least 15.6 kilonewton we have to have there anyway to avoid the structure lifting up. And when it's lifting up, it means everything can lift up and fly away, or it will overturn to the back. That means this 15.6 kilonewton must be ballasted to 100%, 1-to-1. The same what is acting has to be counterweighted by ballast. Then the horizontal parts, this is the tricky one. Basically, there is the combination of these two forces. You can combine them. I guess everybody has heard long back in time at school about Mr. Pythagoras from Greek. And out of the 404, 406 and 13.9, the resulting force is 14.48. And this has to be saved or secured by friction. Usually, I have this presentation, or mostly, I have this presentation in front of groups which are not English native speakers. That's why I start first to explain what friction means. Everybody here, except of the Scandinavians, probably don't know what friction is. So it is basically that you have a kind of force horizontally, and depending on the materials that act or the weight that is applied or which is standing on something, the question is how much force you have to apply horizontally to make it slide. And when you have different materials, pairs of materials, the factor when it starts to slide, at how much force it starts to slide, depends on what kind of material it is. So when you ride with your ice skates with very thin metal blades on ice, the friction is very low. And when you have the rubber tire of your car and push the brake, you have quite a lot of friction between the rubber and the asphalt of the street. And the same is that applies for temporary structures. In the standard for temporary structures, there are described different friction factors depending on what combination of materials you have. So when you have a wooden plate towards a wooden plate, that means wood means that it is raw wood just out of the saw. That is not, that does not have a finish, like a plywood plate, for example. When you have two raw woods, which are just sawed as a flat surface, the friction factor is 0.4. That means you have to apply only 40% of the vertical load to make it slide when you push it horizontally. So when you have 100 kilogram resting on the ground, you have to pull horizontally with 40 kilogram to make it slide. And when it's steel on steel, for example, the friction is less. Then you need only 10 kilogram to make 100 kilogram horizontally sliding. Here, for example, this is now the base of a bigger roof, which is on top of this scaffold structure. And there is any vertical load coming down, and due to the external wind, everything wants to slide somehow. And here are 3 different pairs of material. There's a steel spindle on a wooden plate, then a wood on wood, and then wood on asphalt. That means when we now have to have a look how much force we have to apply vertically to counteract the horizontal acting force, we have first to have a look on the first material pair, which is between the spindle, which is made of steel, and the first wooden plywood deck is 0.4. The next one is between the 2 different wooden pads, and the last one is between the wood and the asphalt. And the weakest one of these 3 is leading. Of course, when it starts to slide, in which gap does it start to slide first? It is there where's the less friction. So that means when we go back to the numbers, the ballast depends on what friction factor you can gain on site. When we have a friction factor of 0.4, the horizontal force of 14.48 is divided by the friction factor 0.4, which means 3.6 tons of ballast just due to the sliding. If it's a friction factor 0.6, it's no more 3.6 tons, but only 2.4 tons. So the higher the friction is, the less ballast you need. And the combination, including the amount of the uplifting force, is either, when you have a friction factor 0.4, it's resulting to 5.2 tons, and when it's friction factor 0.6, it's only 4 tons. Only. Have you ever seen someone putting on an 8 by 6 meter roof 4 tons ballast on the front tower? Most probably not. But this is the outcome of the mathematics and the physics. That's why most people don't ask a structural engineer for support, because the structural engineer just creates paper that costs money and causes problems. But if you want to be prepared for the bad conditions, you should follow the instructions of the structural engineer. Of course, the structural engineer is always looking for the worst case. And the worst case happens perhaps 5 times out of 100 setups. But it's good to be prepared for the worst case. Otherwise, it will either uplift, slide, or overturn. And then you have a lot of loss in money and probably as well in life. You can reduce this amount of ballast by interconnecting the bases between each other. I don't want to go too deep in the mathematics behind, but it's when you imagine the wind is blowing into the front. This wire rope is activated by tension. And this wire rope is going to be slack, because a wire rope cannot take any pressure, usually. That means when you pull on this wire rope, you generate a vertical force lifting up and a horizontal force pushing to the back. This is the 15 and this is the 14 kilonewton. But when you pull on this wire rope and you lift up with 15 here and push 14 back here, you have the same force in this wire rope here on top. That means here is as well the 15 pressing down and the 14 pushing to the front. That means in this tower there's pressure, while this one is lifted up. So when you transfer the horizontal force from here to there by any kind of compression active element, either a truss or a steel beam, or please don't start to use 2 by 1 meter stage stacks which are in between and connect the tower to the stage stacks and then claim that the force can be transferred through the decks to that back tower. No, that doesn't work. As soon as you have a scaffold underneath, yes, that's possible. When it's properly when the roof is standing on top of the scaffold, when it's properly connected to the scaffold, then the scaffold can be used to transfer the forces from the front tower to the back and vice versa. So whatever force you have here pressing vertically down, it can be used to eliminate the force which is coming from the front to the back. This allows you to reduce the required amount of ballast from 5.2 tons to roughly 3 tons on the front tower, and from 4 tons to roughly 2.5, which is already a good benefit, of course. Okay, then now we come to the tricky point. How to connect the ballast to the roof. And about this we can discuss hours and hours. what is good, what is not good. But you have to imagine and to remember the rule always that the ballast must be connected in such a way that any horizontal and vertical movement of the base is prevented. That's the basic rule. It must be connected correctly that the base doesn't move anymore. That's it. How this can look like is, of course, tricky. So when you want to protect against the horizontal movements, first is the ballast should be placed directly in contact to the tower and not even 1 centimeter afar. Because otherwise, first the base will move this 1 centimeter until it's touching the ballast, and then it's activating the ballast. That means you can, just as an example, here it's even not perfectly shown because there's a gap between the pallet with the IBC on top and the base itself. This should be directly in contact, then slinged around with a ratchet. That means then it cannot move horizontally wherever. The protection against the vertical movement, when you have a roof which is equipped with a sleeve block, which can vertically lift and drop, it is saved against drop by the dead hanging mechanism, but it's usually not saved against uplift. That means when you attach the ballast to the base, it does not prevent the uplifting of the roof. That's why you need a vertical wire rope going from the sleeve down to the base, no, not to the base, but to the ballast, to prevent uplifting of the sleeve block. So, going from the ballast up to the sleeve in order to avoid lifting. But if you do like this, what happens here with the IBC? When you lift here, those 2 legs of the bridle will be activated in tension. That means there's a horizontal force acting here, which will squeeze the cage, and after squeezing this cage, it will squeeze the tank itself. Then it will leak, and you don't have your ballast anymore. That means at least here, this is how most people do it, but which is not correct. So if you do so, you should at least add any kind of bar or whatsoever that avoids squeezing of the attach this vertical rope. When you do like this, it's lifting only half of the ballast. Because whatever weight you have, half of it is lifted and half of it is still standing on the ground. I see already people, oh yes, I see what I did wrong all the time. It's good. But don't be ashamed. You are in a group of hundreds of people who make it wrong. So if you go with a vertical rope to the ballast, it should be placed not in the corner, but in its center of gravity in order to lift it entirely, and not only in one corner. Now an example how on a small tower it can look nice, where all these effects are considered. So it is basically a frame which is hooked onto the base. No, I have to first start with the next pictures. So the vertical rope which is coming down has the connection to the frame on which the ballast is standing on. It is in its center of gravity. The next is that the frame which is hooked on the base is, by being hooked on, it immediately avoids any horizontal movements of the base. And finally, on top of the IBCs, there's a crossbar which prevents the squeezing of the IBC. So far, so good? Any questions? Oh, only 5 minutes left. Okay. What about this? When I saw this the first time, my immediate thought was, holy shit. Because first is when, no, it's in the setup status. So when you pull here on this chain, or it's going over there to the guy wire, when it's stretched, when you pull on it, everything wants to move horizontally. The base is connected with these ratchets down to ground stakes. It works perfectly against uplifting. But what about the horizontal? It will just slide under the ratchets. So connecting or securing a roof structure, especially the base, by ground stakes is very difficult. It is possible, but it requires a lot of effort. Next is the very high piled up spreader plates. When you have to pile it up, you have to somehow guarantee that you create a kind of pyramid under the lag, which has a 45-degree angle. And not to make a very slim pile, which simply turns over when soon there's a horizontal load. Another problem with the ratchets is that these screw jacks are designed for the vertical load which are coming out of the roof. But when you stretch the ratchets, you apply an additional pressure for the screw jacks, which is not considered in the report. I talked about the sliding, the huge piled. Yeah, that's it. Now, time is running. I have to hurry up a little. Oh, wait a second. I have time up to 12 o'clock, right? Yeah, then plenty of time. Another example. Very often I hear the question, how much ballast do I need? And this is nothing I can tell you within a second. It requires an extensive calculation. But what is quite easy to calculate, or it's an extensive calculation on the entire roof structure. What is quite easy is this example. Just a wall, 6 by 6 meters, completely closed in the front. And on this example, I just would like to show you the effect of overturning. So when the wind is blowing on the front, the force which is applied is basically the surface multiplied with the wind pressure and multiplied with the force coefficient. And this force coefficient is an aerodynamic factor, and it has something to do with the shape of the structure. You know, what you know from your cars, that a race car has a CW factor of 0.2, 0.25, something like that, and a regular car has a CW factor of how much? 0.8? I don't know exactly. And for this kind of flat wall standing in the wind, the force coefficient factor is 1.3. For cars, it is called CW. For structures, it is called C with an index F. Why there's a difference, I don't know, but I don't care. So, the entire force is the square multiplied by the wind pressure multiplied with the aerodynamic factor, which results in 2.34 tons of horizontal load, which is acting in the middle height of the structure. So now again the side view. And by the way, it is simplified. It does not show the real required ballast. This is where we will get right now. So the 23.4 kilonewton, which equals 2.3 tons, or roughly 5,260 pounds. It is acting in half the height of the structure. So, of course, it is acting everywhere, but you can collect everything together. The entire force is collected together to one resulting load, which acts in half the height. So everything wants to overturn about the rear leg. That means this force multiplied with a lever arm is an overturning moment. And we have to generate enough counterweight to avoid this overturning by adding ballast. And the overturning moment is 23.4 kilonewton multiplied with 3 meters height, multiplied with a safety factor plus 20%. So this is our safety, 20%. And counteracting against this overturning is a so-called standing moment. That means the ballast and the self-weight of the structure multiplied with half the depth. In this case, when it's a 2-meter scaffold size, it is 1 meter, which creates an opposite acting standing moment. And as soon as the standing moment is bigger than the overturning moment, we are done. So then we can set both in an equilibrium and just to calculate how much ballast this must be. 8.4 tons. How can we reduce it? Because I guess nobody wants to carry 500 kilos of scaffold and 8.5 tons of ballast. When we increase the depth by another scaffold bay, the overturning moment is doubled because we have doubled, no, the standing moment is doubled because we have doubled the depth. That means the force which is acting is still the same, the overturning moment is still the same, but the depth is different. That means we don't have, for the standing moment, not only 1 meter acting beneficial, but in this case 2 meters. So that means the 8.5 tons can be reduced to half of it. That means 4.25 tons. Double the depth is 50% ballast. But in this case, as I said, I'm just talking about the overturning effect. Of course, depending on what friction we can gain, if the surface is an ice skating area, or if it is asphalt, or if it is gravel, is it grass, whatsoever. What kind of spreader pad do you have between your metal-made spindle or screw jack and the ground on site? This depends from case to case. It can change from venue to venue. So this must be observed and taken care about in any new installation. That's it already. Any more questions?
Yeah. What's the friction for rubber?
For rubber? It's an endless discussion. Exactly. First is it dry or is it wet? Second is, from a legal point of view, unfortunately, the European standard for temporary structures does not give this friction factor. And I've tried to include this friction factor when I was I attend the standardization committee for temporary structures as well, and I tried to engage the others. Let's include a friction factor for rubber for this, because rubber has a friction factor usually ranging between 0.75 to 0.9, depending on what type of rubber is it. Is it wet? Is it red? Is it wet? Is it slippery? Is it a closed surface, or does it have an open surface? Is it has it a high density or a low density? That's tricky. Unfortunately, we couldn't agree on including the friction factor, and that's why, from a legal point of view, it is not allowed to include a friction factor, but from a realistic point of view, I have nothing against to make friction factor tests on site. That means take a 1-ton concrete block or an IBC or whatsoever, put it on site on the rubber mats that you want to use, pull with it with a forklift, use a measuring device, and then you know how much friction factor you have, what you can gain. But it is organizational work that you have to apply up front. It's not that easy.
This is a question about ground conditions and, like, say if you have a structure with 4 truss columns coming down, 3 of them are in. Yeah, okay. So say 3 of the columns are sitting on grass, where it can be muddy underneath, depending on whether it rains, and it does rain quite a lot here. And say if you have one of them actually sitting on, say, gravel, so when it rains, your friction may reduce, I guess, on 3 of the legs, but not on 1. Or it may sort of settle more because it's a softer material.
Yeah.
How often does that actually occur with stage temporary structures?
There's a difference always between the boring theory I have in my office and the real life you have on site. So I'm lazy. I have my factors and I'm calculating, that's it. I don't want to say that I don't care what you're doing on site. This is wrong. But of course you have to evaluate somehow on site what you are doing. Is it, does the friction change when the weather changes, yes or no? What is more important for me is more than the friction in this case is more the strength of the ground, of the soil, how much vertical load it can accept. Usually we are calculating with a certain stress limit which is acceptable under the spreader pad. So we have a kind of vertical load, and usually your spreader pad on a usual base is about 30 to 30 centimeters, roughly. Then there's the allowed ground pressure, 150 kilonewton per square meter. As soon as you go to bigger spreader pads, you can gain higher stresses, higher acceptable stresses underneath the spreader pad because the force is distributed better to the ground. It's hard for me to find a correct answer for your question. You see, I'm struggling a little. Usually, the friction factors which are given, as far as I know, they consider the wet condition already.
I see. Thank you.
Any other question? Yeah? Over there?
You mentioned about halfway through that horizontal forces could be transferred by a properly made scaffolding, but you said specifically not by stage decks. Can you explain in layman's terms why that is, please?
You mean the difference between a scaffold substructure and a stage deck?
Specifically for transferring horizontal forces.
Yeah. The point is that when you have a regular stage deck, 2 by 1 meters with 4 legs and a pocket underneath. This stage deck is designed to transfer the vertical loads of the people standing on it, including a certain amount of horizontal load. As soon you try to connect this kind of stage deck to your stage in order to transfer the loads from the front base to the rear base, you not only transfer the force through the deck itself, the legs underneath will bend because of the horizontal movement. That means the horizontal and the vertical legs of the stage deck will first allow a lot of deformation because of its elasticity. And second is that at a certain point, the horizontal movement which will occur will be such high that the legs will fail. That means the front tower can move while the rear will still remain somehow. So it has something to do with elasticities between the towers and the deck in between. So if you want to transfer the force from the front to the rear tower, you should have a proper element that is connecting from base to have a direct load path from the Y rope to the base, from the base through the beam to the rear base. And from the rear base to the ballast which is standing next to it. Okay? Anything else? Wait a second for the microphone.
I was just going to ask, the wind loading that you mentioned, what does that equate to in actual wind speed, and does that change over time with our current climate?
The wind load I've mentioned in the calculation for the scaffold wall was 0.5 kilonewton per square meter. That means 50 kilogram per square meter, which equals a wind load 101 kilometers an hour, which is the limit which this structure, which was only 6 meter high, would have to resist from a calculational point of view. I accepted for this example that the cover on the front of the scaffold wall will not be dismantled at a certain wind speed limit. Usually when you have a roof structure, there are two different status for which it is calculated. That means the first in-service status. That means all the 3 walls are covered and the rooftop is covered, and it's collecting the wind load. At a certain wind speed level, which is usually 20.6 meters per hour, you have to start, now you have finished the work to disassemble the walls in order to reduce the area that can collect the wind. So, yeah, a roof structure is calculated in 2 different status. In service, completely covered. Out of service with dismantled side walls that the wind can pass through. Does this answer your question? Kind of. Okay. Anything else? We have 3 minutes left.
With a lot of structures, there's obviously different action stages depending on wind rating, and a lot of the time it's, as you just talked about, taking the walls off. Obviously a lot of the time they're connected by cable clamps to things up in the roof, so the only way you could do that is to either drop the structure or try and climb a structure that's becoming unsafe. So
that's one point.
The best course of action?
First point is when you start to, you have to create upfront an operational management plan for your roof that describes what activity, what action do you take in case of bad weathers. And this high wind action plan requires feasible actions, which are not only nice when written on paper, but they must be feasible on site as well. So doable. And climbing in 74 kilometers an hour, a roof structure, when you make a proper risk assessment, you know that it's not a good idea. I've met riggers who told me, yes, at 6x4 plus, rigging makes fun, but that's not proper risk assessment. So whatever action you do, you have to be able to process these actions to disassemble the walls from the ground. That means you have to set up some mechanical solutions to release the wall, either when it's guided in kidder profiles that you can release it on the bottom and just drop it or pull them down, or when it's connected to the towers, to the back truss, to the towers again. Then there are different techniques how to connect it to the towers with a special knitting or, how is it called when you make your socks? Yeah, when you release the first node, the first knot, then everything else is releasing itself, and then it's falling down automatically. So that was the first part of your question, and the others?
No, it was just that. So I've got into particular 2 structures where the manufacturer advised wind ratings is that at this point you take the walls off, and at this point you do this. But because of the way that they have been made and the way that the walls are supported on, the only way you would be able to remove the walls is you have to climb the structure to fix them on, so you'd have to climb the structure to fix them off.
Then I guess you have to upgrade your structure to create some kind of solution that does not require climbing.
That's great, thank you. Well, scary bit is one of them is only a year old.
So since you mentioned like the kind of like fluid mechanics like coefficient, right? So is it like, you know, like in race cars, like the back fin of the race car is actually able to like redirect the wind to produce a downward force. Is it possible to add fins to the top of the roof, or change the different shape of the roof to mitigate the upthrusting?
Sounds like a weird but interesting idea. Actually, the problematic of the usual roof structures, either when it's a pitch roof or when it's a saddle roof, the shape behaves some kind like a wing of an airplane. So when you have a saddle roof structure, the wind is blowing around from the side, and it's going over the top, and the way over the top is longer than horizontally underneath, so there's an uplifting force anyway. Your idea to create some wings to press it down, I guess the efforts you have to make to generate this will not be economic. I think so. But it would be an interesting design. Probably we should think about it. If we find people who likes that design, I don't know. But you're right. The back wing on a race car does nothing else than generating pressure in order to increase the force on the wheels to allow it to drive faster through the bend by having more friction, or by that they can drive faster through the bend with more horizontal load, but the friction is still the same between the tire and the asphalt of the racetrack. Anything else?
You need to design some stage spoilers.
Sorry?
You need to design some stage spoilers now.
Yeah, when there are no more questions, we are out of time. Thank you for coming. Thanks for your attention. I would love to see you back tomorrow for another presentation, which I will have together with this nice gentleman in the front row. We will talk about the needs and the difficulties what the manufacturer and the user have to take care of when purchasing a new roof structure. Thanks a lot for your attention. See you tomorrow, hopefully.